So the first step of air pollution control is pollution prevention. And it's kind of difficult to satisfy pollution prevention for all the compounds we're looking at, especially because some of them form under conditions where the other ones are controlled. So nitrogen oxides, for example, are formed at high temperatures with high oxygen. And there's some ways around forming these, basically by limiting the amount of excess oxygen that's there, and that just makes it less likely that a nitrogen is going to grab a stray oxygen and react with it. So using staged combustion, low excess air, and flue gas recirculation, so taking some of the oxygen out of the air that's coming out of the reactor, these are all ways to keep the oxygen low and try and prevent you from forming nitrous oxides. Carbon dioxide or carbon monoxide is formed in low oxygen, so it's an incomplete combustion product. So you can see that nitrogen oxide forms at high oxygen, carbon monoxide forms at low oxygen. So you have to find a balance point in between the two since they form under different conditions. Carbon monoxide would be addressed by adding a lot of aeration and mixing and making sure that it got that other oxygen and react into the carbon dioxide. Dioxins and furans are kind of similar to carbon monoxide. They form in a low oxygen environment and they form in a specific temperature range, 400 to 700 degrees Celsius. So the approaches to limiting dioxin and furan formation are like carbon monoxide, make sure there's enough air and mass transfer that they can mix well and oxidize into carbon dioxide. And then also, once the flue gas comes out, you want to quickly cool it to below that 400 to 700 range, so they're not going to reform in the flue gas coming out afterward. So you can see there's some common things across these pollution prevention approaches, and there's some where different approaches wouldn't work for all of them, and that's why it's important to have our pollution control technologies downstream to sort out the things that we can address just with pollution prevention alone. Here's just a figure showing the dioxin control hierarchy. So the equipment that's used to cool down the flue gases right at the beginning, and then all the downstream equipment that can be used to remove some of those dioxins once they form, if we weren't able to address all of it through the pollution prevention approaches. With our long list of pollutants that we want to remove, we have a long list of technologies that need to be applied if we want to remove all of them. So these include, for nitrogen oxides removal, either selective catalytic reduction or selective non-catalytic reduction, acid gas removal, which uses different types of wet and dry scrubbers, mercury, which is removed through adsorption with carbon or sodium sulfide, and then lastly, particulate matter removal. And this would apply to some of the particulates generated by some of the earlier processes, as well as the particulates coming off of the waste from the combustion chamber. For acid gases, the best way to remove them is to contact them with a basic solution, which will neutralize them into a soluble salt. And then when it's trapped in that scrubbant, the scrubbant can be regenerated or disposed whenever it's saturated with acid gases. So we've seen some of these designs before. On the left is a packed tower. On the right is an atomized mist sprayer. So these are both designed just to maximize the mixing between the gas and the liquid phases to really get a lot of contact between those two phases. Another way that you can get that high contact shown on the left here is a Venturi scrubber. So rather than kind of spreading everything out as with the packed tower and the atomized mist sprayer, they squeeze everything together through a Venturi nozzle. So that forces everything to come together at high velocity, and that generates the mixing that contacts the treatment stream with the scrubbant. And then the water droplets will be able to drop out by gravity and leave the clean air stream. And then one last similar technology is called a spray dryer. So it's kind of similar to the atomized mist sprayer in that it's spraying a liquid, but rather than recovering the treated material as a liquid, the solution of the scrubbant and the treatment material turn into a dry solid, and then that dry solid is cycloned out and it leaves the clean gas to come off the other side. A dry sorbent injection is doing a similar thing. It's just using a solid from the get-go and then contacting that, again, trying to maximize that contact with the gas phase. And then the sorbent that's reacted with the treatment compound will be removed with a filter or baghouse later on, and then the treatment stream comes out. Each of these technologies, the dry sorbent, the Venturi scrubber, the spray dryer, and the wet scrubbers, are all focused on contacting the acid gas in the flue gas with some type of solution that will react with it, and then removing it either as a liquid, as in these ones, or as a solid in the latter two. The next thing we can talk about is mercury, dioxins, and furans, and these are treated with a solid sorbent. So carbon, we know, is a really great sorbent. It'll absorb both mercury and dioxins and furans, and carbon can be contacted with an approach like the dry sorbent, where it's added as a powder into the flue gas, or it can be a fixed bed filter like we saw for the odor treatment systems. Another compound that's effective for mercury is sodium sulfide. So sodium sulfide reacts with mercury in the flue gas to make mercury sulfide, which is a solid, and then that solid can be removed later on. And mercury sulfide is also called cinnabar. It's actually a red pigment that's shown at the bottom. So now we might have some particulates in our stream from treatment, plus our particulates that actually came from the combustion reaction, and we'll look at a few technologies that remove those particulates. So one of the workhorses of particulate removal is called a baghouse, and it operates a lot like a hollow fiber filter turned inside out. So the air is pumped up through the bottom of this of these bags that are all hanging in this enclosure. And then the solids are retained on the inside, and then the air is able to pass through the pores. So eventually this will get caked with solids, and there's a shaker mechanism that will kind of shake them out, and it'll fall into this hopper, and then you'll be able to drive a truck underneath and collect it all and send it off for treatment. So this is our fly ash, all this solid that's being removed directly from the flue gas. An alternative particulate removal technology to the baghouse is called an electrostatic precipitator. And baghouse is more efficient at kind of removing large bulk amounts. So an ESP would be better for a stream where there's less particulates, or maybe downstream of a baghouse for a polishing step. And how it works is that it uses charged wires or plates to pass negative charges onto solids that are floating through the airstream. And then there'll be a coinciding pair of positively charged plates that will attach these now negative particles, and then those will periodically shake, and the solids can be removed that way. It can use either plates or wires as a way to get high surface area contact with the gas stream. Next, we have technologies for removing nitrogen oxides, and these can be selective catalytic or selective non-catalytic reduction. And it's called a reduction because it's a redox process. So we use a reducing agent, which is a reduced form of nitrogen, and that can either be ammonia or urea. And then the oxidized form of nitrogen is the nitrogen oxide. So the reducing agent reduces the oxidized form of nitrogen and leaves nitrogen gas, which is safe to go off into the atmosphere. And then the other product should be water, which uses the hydrogen from the ammonia or urea, and then the oxygen from the nitrogen oxide. So both types of reactors target this redox reaction, but they happen in different ways. So selective catalytic reduction is the one shown on the left of the picture, and this happens outside the combustion chamber. So this would be our incinerator. We have our flue gas coming out. Here they've got cooling, capturing the dust. And then at the end, we've got this catalyst bed where they're spraying in the reducing agent, and we're getting that contact between the nitrogen oxides in the treatment stream and the reducing agent, and those should react to form that nitrogen and water, and then our clean flue gas comes out. With selective non-catalytic reduction, rather than having the reaction recur over this catalyst, we have the reaction occur at a higher temperature, and that's done by injecting the reducing agent right into the combustion chamber, somewhere upstream of where the actual combustion reaction is occurring. So it needs to be at the right location, but the idea is that these reducing agents will have a greater affinity for the nitrogen oxides, and they'll react using the temperature of that instead of requiring a catalyst. So it can be a more economical way to achieve some of the nitrogen oxide reducing effect that this technology is meant to have. Lastly, let's take a look at one case study. So this is Emerald Energy from Waste Air Pollution Control System. This is Ontario's modular incineration facility. So you can see in the process flow diagram on the right, there's the 5 incineration modules, and then the 5, they're called boilers here. These would be the secondary chambers where all the gas is burned. So what we're interested in is everything downstream of that. So in the schematic here, you can see first all the gas goes through evaporative cooling towers, and that's to cool it down. So we're not in that zone where we can form dioxins and furans. And that's this first chunk here on the plant. The next place we go to is Venturi reactors, and the reactants that are being added here are activated carbon and lime. So lime is basic, right? It's going to react with our acid gases, and then activated carbon is a good general sorbent, which is going to react with mercury, any dioxins and furans that have formed, and anything else that hasn't been treated. So those all get contacted in the Venturi reactor. And then coming over, the next thing here is the baghouses. So that's where all those particulates that we just formed in the Venturi, as well as anything that was coming out of the incinerators, can be pulled out from the baghouse. So now we're over here in the baghouse. And then our last piece here is the selective catalytic reduction system to remove any nitrogen oxides that are remaining. And interestingly, they have a little burner upstream of that to help heat the gas back up. So it's actually too cool by the time it gets here. So they heat it back up again, and they also add ammonia as the reagent to reduce that nitrogen oxides into nitrogen gas. And then the final step is coming out this stack at the end.